videocast, we're going to talk about the most probable location for an electron within an atom. We know that the electrons are not located within the nucleus, that they are located outside of the nucleus in the electron cloud. We also know from Bohr's model, or what we took from Bohr's model of the atom, is that these electrons do exist in energy levels, or certain distances from the nucleus, and not in between those certain distances. Now, they are not like Bohr thought, where they are on these little rings and they just rotated like planets rotate around the sun. It's a little more weird than that. Around 1925, we had Erwin Schrödinger, who came up with a wave function of an electron, and the solutions to his wave function, which is a giant calculus problem, are called quantum numbers, and they describe the most probable region to find an electron within an atom. And by the end of today, we're going to learn how to describe the most probable location for an electron, for every electron. So like I said, these quantum numbers are the solutions to Schrödinger's wave function. Now, there are several principles and rules that you must know as we go through this chapter. The first one we're going to get to right off the bat, the Pauli exclusion principle. Pauli exclusion principle says that no two electrons have the same set of 4 quantum numbers. Those 4 quantum numbers describe the location of an electron, just like a zip code describes the location of a town. So what we're going to do is, and no two towns can have the same zip code, no two electrons can have the same set of 4 quantum numbers. All right, so go ahead and make sure that you're remembering that one. The first quantum number is called the principal quantum number and is represented by the symbol N. So anytime you see N equals 1, N equals 2, N equals 3, then they're talking about the energy level. And again, those are distances from the nucleus. So if I have a nucleus, and then I have my energy levels around that nucleus, and this picture should look very familiar from like middle school. We number those from the nucleus out. So N equals 1 would be the closest to the nucleus, and that would be our first energy level. N equals 2 is our second energy level, and N equals 3 would be our third energy level, so on and so forth. Now that's probably as far as you've ever gone with mapping electrons, but we can go even further with that. All right, second quantum number is that called the angular momentum quantum number. It is represented by a cursive L, and it is the sublevel, or what I will refer to as the sublevel. It is technically the shape of the orbital, and you need to make sure that you know that. Now, an orbital is a mathematically drawn shape where a region of probability, where an electron is most likely to be found. And they have different shapes, and we have 4 different ones, and each one is a different shape. The S sublevel is a sphere. The P sublevel is a dumbbell shape. A D sublevel is basically a 4-leaf clover with an exception. And I say F stands for funky. We don't have to know what the shape of that is. So I'm going to show you what these look like here. All right. So here we have a S sublevel. It is a sphere around that nucleus, and the electron is located somewhere within that sphere. This is a P sublevel, and the technical name for this shape is a dumbbell shape. D, for the most part, looks like a 4-leaf clover. And here's a representative from F. It almost looks kind of like a flower in this one. We'll look at some of the other orientations here in a second. So they're going to narrow down where that location of the electron is just a little bit more. The third quantum number is the magnetic quantum number. It is M sub L, and that is a cursive L there. And it deals with the orbital orientation in 3-dimensional space. So how it is oriented. I've got some pictures of that to show you. So that S, there's only one way to orient a sphere in space, And so there's only one orbital orientation for an s sublevel. A p sublevel, we have three different orbital orientations. We can have the p sublevel along the z-axis, we could have the p sublevel along the x-axis, and we could have that shape, that dumbbell shape, along the y-axis. So there are three different orbital orientations for a p sublevel. D has 5, and you'll see most of those do look like four-leaf clovers, with the exception of this one, which I think kind of looks like a double pacifier. And then we have F. It has 7 different orbital orientations, and most of them kind of look like a flower, except for this one over here, so it gets even more weird. Again, these shapes don't really exist within an atom. They are just mathematical areas of probability on where we're most likely to find an electron. Our last quantum number, and there are only 4, is the spin. It is represented by m sub s, and spin has 2 values, either positive 1/2 or negative 1/2. Is the electron spinning clockwise or counterclockwise? That's what those values mean. Now, chemists are incredibly lazy, so instead of writing positive 1/2 and negative 1/2, sometimes we just write up and down arrows to represent those.